So what are we trying to learn today? We're trying to learn the roots of why SN1, SN2, and how to study it in terms of a kinetic thing. You know what this chapter actually is more about? It's about refining what we learn. Like in Gen Chem, we learn that a triple bond is shorter than a double bond. But here in Orgo, we refine that and say it's not because of the number of sticks, it's because of the S character, right? You're all on my wavelength here. So in Gen Chem, we learn that if you have a reaction, let's say 2A goes to B, it has a specific rate constant, yes? And you could write a rate law as rate is equal to K times the concentration of A to the nth power. It doesn't necessarily mean a 2 because we don't know if that's an elementary step or not. So you could write a rate law like this, right? Do you remember there was another way to express the rate? There was this way to express the rate. You could say that was relating the rates or monitoring the rates. You could say the rate is equal to the negative 1/2 change in concentration of A divided by change in time. Anybody remember this? And that also equals the positive 1/1 change in concentration of B over change in time. I'm just showing you what we saw in Gen Chem, and I'm going to show you how this chapter is deeper than just learning some reactions of SN1 and SN2. It's learning a greater depth of chemistry, of rate-related chemistry. And they're showing it to you through the eyes of like what we call substitution reactions in organic chemistry. Right? So we're really not trying to figure out what the answer is. What does a product look like? Because that's not going into the depth that we're trying to do. A lot of us don't remember this. A lot of us barely remember this. I have this experience over years, so I'm trying to remind you that when you write a rate law, it's some rate constant, some specific rate constant, multiplied by the reactants, not the products, the reactants. And if it's a one-step thing, then the coefficient is the power. And if it's many steps in the mechanism, then you don't know what this is. And that's why you have to do various experiments. They show you, remember, they had like 3 or 4 different experiments where they varied the amount of A, and they have various rates. And if you double A and the rate doubles, then it's to the first power. If they double A and the rate squares, or quadruples, let's say, then it's to the second power, and so on. What was that about? It's because this is the rate law. This is what is obeyed, but this is not what you see. In a flask, you've got to follow a rate, and in physics, a rate of change, for example, in Physics 1, you learn about a rate of change like speed. It's a change of something. That's the worst thing to say, right? What do you mean something? It's a change of some quantity in a change of time. For example, my speed, my rate of travel, is my change of distance divided by change of time. I could have an acceleration, and that acceleration, the rate of how I'm accelerating, is the way I'm changing my speed in time. I could have a rate of a reaction, and that rate of a reaction is how many reactants react in some amount of time. That's like how many reactants, the change in the reactant concentration in time, or the change of the product concentration in time. Are you somewhat seeing the connection here? Let's make a slightly simpler connection. Let's say I work in a sandwich shop, right? And I have 2 pieces of bread and 1 slice of cheese makes a really crappy sandwich, but imagine I am the owner of the shop. I've got a lot of people working for me building these sandwiches. And I'm just walking around with like a clipboard and a pen. I'm trying to monitor the rate. Why would I monitor the rate? Because I don't want to run out of bread or run out of cheese. I need to figure out when to buy, when to place the next order. Imagine I have a stack of bread and a stack of cheese. Imagine there's 100 pieces of bread and 100 pieces of cheese. The rate of building sandwiches is going to be the same whether I look at the bread pile or I look at the cheese pile, but I'm going to see the bread pile disappear faster than I'm going to see the cheese pile disappear. Because every time I make a sandwich, 2 breads go and 1 cheese goes. 2 breads go and 1 cheese goes. 2 breads go and 1 cheese goes. At it's not a better rate for bread and a better rate for cheese. It's the same rate. It's just that in the reaction, it's 2 breads to 1 cheese. So if I want to know about the rate of production of sandwich, what I have to do is divide the rate that the bread is going by 2, or divide the rate that the cheese is going by 1. And either way, that would give me the same number where I look at the bread pile or look at the cheese pile. Do you see that? You see why I have to have half? Because if the coefficient is 2, we're monitoring the rate. Here's a question that often students get wrong. Not wrong in like a totally wrong way, but in a very kind of nitpicky way. Why is there a negative over here? Those of you that did well in Gen Chem 2 are going to give me the wrong answer, but an almost right answer, but a wrong answer. It's the exact words I wanted to hear. That's the wrong answer, but the right answer, but so the answer was because this is disappearing. Absolutely true. But that's not why there's a negative there. It is disappearing, but that's not why there's a negative there. It's because the rate has to be a positive value with molar on the top, and usually it's in seconds, but it could be in minutes or something like that. So let's say molar per second. The rate has to be molar per second. And if I'm going to take the rate of watching a reactant, you're right, the reactant is disappearing. Like if there is some amount of reactant at time equals 0, then at time equals t, some later time, there's less reactant because it's getting used up, right? And if I take this value, because change is final minus initial, if I do final minus initial, I get a negative value over here. So it's not just because it's disappearing, it's because I need a positive value for my molar per second. So if this is negative, then I need a negative in front of that negative to make that a positive value. So it's sort of like saying it's because it's disappearing is sort of like saying it's because there's 3 bonds. Well, it's actually because of S character. You see, it's not as refined an answer. We can watch something disappear. We could watch something appear. You've done it. You had a lab on crystal violet, for example, watching things disappear or reappear. Did anyone do a lab on crystal violet? Chem 2? We could monitor a reaction and just watch how A changes in time, or watch how B changes in time, and it'll obey this rate law. And I'm reviewing Chem 2 to show you how Orgo picks up where Chem 2 left off. One important detail, we already said that there's a negative there, partly because this is disappearing and therefore you want that to be a positive rate. So if it's disappearing, then you're going to see the amount of A in time decrease. But how's it going to look? Is it going to look like that decreasing? Is it going to look like this decreasing? Is it going to look like that decreasing? Which one of those curves is the correct curve for decrease? No matter which reaction it is, one of these is the correct curve. And the correct curve is the logarithmic decay, y. Why? This is so important. It has so much to do with being able to read this chapter. Let's say this was to the first power, or to the second power, or to the third power. It doesn't matter what power this is. Here's something that's true. I'll just keep it to the first power because it's the easiest to see. Do you see the rate would change in time? If I start with a lot of A, and that's a constant, that's a specific rate constant, this number doesn't change. But in the reaction, this number gets smaller and smaller and smaller as the reaction proceeds, right? Do you see that? So if this number stays the same, but this number decreases, that means the rate decreases. Is that true so far? And if the rate decreases, and the rate is change of A over change in time, when I put A over here and time over here, what is the rate? This is not a difficult question. I'm asking a graphic question, a question about a graph, not a chemistry question. I'm asking a question about a graph. You see change of A over change in time. Where is A and where is time on this graph? Look, open your eyes. Where's A on the graph? On the y-axis. Where is time on it? X-axis. So a change of A, and A is on the y, that's a change of the y. over change in time, and time is on the x, that's a change of x. What's change in y over change in x? Now let's put the thoughts together. Because A is decreasing in time, the rate is decreasing in time. But when you graph concentration versus time, then you're looking at the rate in this concentration versus time kind of a way. And if rate is decreasing, that means the slope should be decreasing. And over here, you have a big slope, and over here, you have a small slope. Do you see that's the only curve that shows a decreasing slope? This curve shows an increasing slope. Do you see that? Well, absolute value increasing. I don't mean it. They're all, both this and this is an actual decreasing slope, but absolute value-wise, this is a decreasing slope. That would be an increasing slope. Yeah. Say that again? The graph of B, it would be the inverse. It would be like that. Because in the beginning, you would be making the most B, and then you'd be making less B, because that's each A changes a lot, B changes a lot, right? And when A slows down, B slows down. Do you see this? Okay. Then in Gen Chem, we're very close to starting nucleophilic substitution. Then in Gen Chem, we said, okay, what if you had two different reactions? And they had the same kind of reactant, let's say. Any reaction out of a bigger rate would have a larger K value. Are you with me? So if you have the same concentration in two different flasks, for example, let's say I have A in this flask, and it's 1 molar. And I have A in this flask, and it's 1 molar. But this flask, I keep calling it a flask, it's a beaker. But this beaker, I heat up. And when I heat up, I increase the rate of the reaction, right? Well, I've changed the rate, and I didn't change the A. That means I've changed the K, right? And you would say, since in here it's happening faster, this has a larger K, and this has a smaller K, right? And temperature affects K. That's all you learn, that temperature affects K. Now the point of SN1 and SN2 is to look at what other things affect K. This is the entire point, in my opinion, of this chapter. Besides learning Orgo, you're also learning Gen Chem, all at the same time. Refining what you know about the specific rate constant. So, if you watched the video, you learned that you could do a substitution on a carbon, but it actually turns out it doesn't have to be a carbon. It could be any tetrahedral atom. Did you notice in the video I said it has to be a tetrahedral atom? I drew it right up here. You had the ability to watch this video 500 times if you wanted. I put a box over here. I said any tetrahedral atom. So it could be a carbon. And if it's a carbon, it could have various groups on it, like R double prime, R triple prime. This just means they don't have to be the same. This could be a methyl, this could be a propyl, that could be a hydrogen, who knows what they are. But this would be a before picture where you have in your flask a nucleophile, and then that, whatever a nucleophile might mean. And then an after picture would be that some exchange has taken place. And instead of being attached to the leaving group, the carbon is attached to the nucleophile. But don't get me wrong, if this was an sp2 carbon, like that, you could do an exchange over here. It just won't be called SN1 or SN2. It'll go by a different mechanism, and it's to be learned in Orgo too. So there's an exchange taking place over here. And we think about the rate regarding how this exchange is taking place to figure out whether it's SN1 or SN2. Is an additional thing I should have mentioned, that like if you have a reaction A plus B is in equilibrium with C plus D, and then let's say C plus E makes F plus B, This is a mechanism. This is a multi-step process. And if you add everything up, then you have A plus B plus C plus E makes C plus D plus F plus B. Do you see that B cancels and C cancels? And it's really A plus E makes F plus D. That's the overall. Could you draw a transition state for this? No, thank you for saying that fast. Absolutely not. You can't draw a transition for the whole reaction. A and E don't react with each other. E reacts with C. A reacts with B. Except B is a catalyst, C is an intermediate, and the rate of this is the rate of whichever step is slow. And let's say this is the slow step. Then the rate of that is going to be the rate is equal to K times the concentration of A times the concentration of B, each to the first power, because that's an elementary reaction. And if this happens to be the slow step, then we have a problem, because we can't have an intermediate inside the slow step. That's what I avoided saying in the video, because it was a fast video. I wasn't trying to teach you all of Chem 2. But you can't put an intermediate in a rate law, partly because we don't even know the existence of the intermediate. Now we have equipment that actually can show us the existence of a carbocation, for example, but they didn't know. You put reactants in a flask, you get products out of the flask. How could you make a law on something that's a proposed intermediate? You can't make a law against it. So you're going to have to do something called a steady state approximation, which maybe you guys learned in Chem 2. We're going to definitely learn in terms of enzyme kinetics in biochem. The question here is, how do you guess a mechanism? And the answer is, you could guess anything, but what's an educated guess? What has changed in this process? This bond breaks. This bond is made. And when it comes to breaking a bond and making a bond in time, we're worried about what happens in time. You have two events. You could have one happen first, then the other one happen, or the second one happens and the first one happens, or they happen simultaneously. If the bond first breaks, then you will get a broken octet on carbon. You will have less than an octet. There's a couple of ways it could break, by the way. It could break homolytically or heterolytically. If it breaks heterolytically, both of these electrons go onto the leaving group, you get a carbocation. If it breaks homolytically, one electron goes to each side, you get a carbon radical. We'll be dealing with that in later chapters. But here we're trying to do things simply. So since you see two electrons on the nuke and now a bond, we're just going to say, let's do this 2 electrons at a time. So either both of those electrons leave with the leaving group and give you a carbocation, then the nuke comes in. So you have the option of break, then make. Break a bond, then make a bond. And do you see how that's 2 steps? And draw a step where the bond to the leaving group leaves. That's 1 step. And then the nucleophile joins in. There's a guessed mechanism. Another one is make the bond first, then break the bond. How could you do that? Imagine the nucleophile attaches, stays that way for a while, and then the leaving group leaves. And then the third one is simultaneous. And as long as that's a carbon, way number 2 is impossible. But if that was a silicon, let's say, or a sulfur or something like that, then way number 2 is possible. Because carbon can't have something attached to it. That goes back to our first lesson. We can't go above the octet. We could go below an octet, hypothetically. You could go to a carbocation, hypothetically. We've seen a carbocation intermediate with an alkene and HBr. But you can't put 5 bonds on carbon. That doesn't work. If that was a silicon, then we would have 3 different possible mechanisms. This is the easiest of things that we're going to study because there's only 2 events, a make and a break. There's much more events with alkene and HBr. There's a couple of bonds that are made and broken. In more complicated systems, you might break 3 bonds and make 2 bonds. Do you see how many combinations are? With 5 events, 2 of them could happen at the same time, then 3, or 1, then 3, or then 1, then 2, then 1, then... You could come up with 5,000 different mechanisms. So it's easy when there's only 3, and one of them can't even happen. If you break, then make, that's 2 steps. And if you do it simultaneous, that's 1 step. So it's always interesting that the one that's 2 steps is SN1, and the one that's 1 step is SN2. 2 to 1 and 1 to 2, but that's not why it's called SN1 or SN2. SN1, you know, I watched the video again, I realized maybe to somebody who's not paying attention, it's not clear. I draw a dividing line, and I'm showing before and after, but up here I have SN1, and over here I have SN2. I'm not saying before is SN1 and after is SN2. If you listen to the words that I am using, I'm saying we have SN1 and SN2, but ignoring them, generally, both of these happen. This happens in both SN1 and SN2. It's just how it happens, the order of steps. See how long it takes for us to boil. So you have SN1 and you have SN2. And when it comes to SN1, it's called substitution, nucleophilic, unimolecular, and it's called that because it's a unimolecular rate law, which means you're going to have rate is equal to K times only the concentration of one thing. If it be to the second power, that'd be two things. If it be to the third power, it'd be three things. If it's three things, you could say it's trimolecular. If its rate is equal to K times the concentration of A times B times C, that's also three things. So why is it unimolecular? Because of this reason. You have a carbon with, let's say, R, R prime, R double prime, and a leaving group. Don't get confused. Before I wrote prime, double prime, triple prime. Now I'm writing R, R prime, double prime. I'm just trying to show they're different. It doesn't matter how you symbolize it, right? Okay. And if it is this unimolecular way, then it's the two-step thing. This happens in two steps. And in the first step, the bond breaks first. And the bond always breaks in this way. The leaving group takes the electrons with it. You end up with a carbocation. Make sure to say carbocation. People call it carbocation, and that's the worst thing in the world. Next to Renaissance structures. The leaving group just leaves. That's what's going to happen, right? A week from now, people will be like, I don't get it. The leaving group just falls off. Well, I explain here, just like in the video, I explained what factors lead to the ability for a leaving group to leave. I'm going to discuss it a little bit more in a little greater detail here. But notice, if the leaving group manages to break off, then we have a carbocation, and then we have, who cares that it's called a leaving group? Do you see it's a base? Do you see it's got a lone pair negative charge? That's a base. And just like if we had a carbocation and a Br minus, and I know that might have come from an alkene, an HBr. Who cares where it came from? If this is hanging out next to this, do you see how it can attach and make a covalent bond? That's why I have a reverse arrow. That leaving group could come in here, attach, and go right back. That's one possibility. But if I have something called a nucleophile in the flask, then that carbocation, that same carbocation, drew it too big. That same carbocation could interact with the nucleophile. For ease of presentation, I'm going to show the nucleophile is a negative thing. In many cases, the nucleophile is neutral, and it's not going to be two steps. It'll be more than two steps. But that nucleophile will attach to the carbon, and notice it's one single arrow, where you have R, R prime, R double prime connected to the nuke. And this is step one, and this is step two, and what we're worried about here is the rate determining step, because the rate determining step will give us the rate law, and that rate law should be unimolecular. So you could already know ahead of time which is the rate determining step, because if this is the rate determining step, then there's only one reactant, and that's unimolecular, and if this is the rate determining step, then this is two reactants, and that's bimolecular, and we already know it's unimolecular. Why is this the rate determining step? Because it's more difficult to break the octet rule than it is to complete the octet rule. That's part of what my assignment was with the alkene and HBr. Did you get the fact that that first transition state was like the product, but the second one was like the reactant? I hope you got that. There's going to be stereochemical considerations here. And what you have when you have an SN1 reaction is your product is going to have racet. Careful with this arrow that I just drew. This has nothing to do with the reaction. I should do this. different color, because it's not pushing arrows. I'm just writing a word here. You get racemization. Anybody read about that? That you get SN1 gives you racemization? Hear about it in recitation and all that? Okay. Yet it doesn't mean what most people think it means. It doesn't mean you get a racemic mixture. What it means is that you get racemization at the carbon that's attacked. Writing that down is useless. So why don't we get a clear image in our brain of what it actually means? That's tetrahedral, right? sp3. Now let's say this is methyl, methyl, and methyl, and that's a leaving group like a Br. Then over here you have no stereochem. But let's say that's methyl, let's say that's a hydrogen, and let's say that's a propyl, and that's a Br. You have 4 different kinds of groups. That has stereochem. And let's say I drew it on a wedge and a dash, it could be either R or S, right? So you have some sort of stereochem. When that leaving group leaves, if this was, let's say, S, and that leaving group left, what is it now, R or S? It's a nothing because it doesn't have 4 groups. It's sp2. It doesn't have R or S. Good. Now what does it look like? This isn't SN2 yet. It's trigonal planar. So you've got an R group this way, let's say, an R group in front, an R group in back, like prime, double prime, whatever. And you have the unhybridized p orbital above and below. We used this picture to demonstrate hyperconjugation before, right? Yeah. You have a nucleophile. I need you to picture this because I really don't want to draw both. So just I need you to envision, I'm going to show you. This nucleophile is going to make a bond. The electrons are in an orbital. That orbital is going to overlap with either this orbital and make a bond on top, or those electrons are going to overlap with the orbital down here and make a bond on the bottom. If it makes a bond on top, these 3 groups go down, and you're going to have a tetrahedron with the nuke on top. If it makes a bond on the bottom, you're going to have a tetrahedron upside down with the nuke on the bottom. Do you see that if these 3 groups are different from each other and the nuke attaches on top, you could get either R or S, and when it attaches from the bottom, you could get the other one, either R or S. Can you picture that? But that doesn't mean you get a racemic mixture. That doesn't mean that at all. So I'm going to give you right now 3 examples of what racemization is. And I don't want you to fully try to understand SN1 because we didn't describe SN1. I'm going to give you 3 cases that all go SN1. I don't want you to stare at it like, how do I know it goes SN1? I need you to cycle my notes also, by the way. There's things that I've cooked into your notes that if you look at it a second time, you'd be like, oh, shit. That's interesting that he said that. I didn't even catch that he said that. So your job right now is to try to help understand what racemization means, right? And it means that you don't get a racemic mixture, but what you could get is products that are either achiral, so it's the same thing. When it attacks on top and bottom, you could end up having the same molecules. Or you could have a racemic mixture, or you could have diastereomers. So you know what this really is? When you attack from the top or bottom, it's that test question, which is, are these the same? Enantiomers or diastereomers. Do you remember that test question? Right? So rather than be worried about, did I get it right on the exam, worry about the concept, because forever we're going to have to use that concept of, is it the same, enantiomers or diastereomers? So just watch the examples. See if you could see. If I have this compound right here with a leaving group, Br, I didn't describe yet what a leaving group is, so whether you know that Br is a leaving group doesn't matter. It's not part of this thing. By the end of today, we know why Br is a leaving group. And I put it in SN1 conditions. Now, why is water SN1 conditions? Who cares? Just agree with me that it is for now. Bless you. Agree with me that it is for now. Okay? We're going to get a replacement. Now, based on what I've just said over here, whether that's got like a wedge or a dash, when that leaves, you got a trigonal planar thing. And then when the nucleophile comes in, it could come in from both sides, so it can become wedge and dash. So if that's a dash, it could be wedge and dash, and if that's a wedge, it could be wedge and dash, right? So the point is, you're going to get the following. You're going to have OH over here, and you're going to have OH over here. Why is it an OH? We'll learn SN1. It's not the idea. The idea right now is the stereochem. What if I had this compound? And I treated this with the same H2O. It's almost the same exact chain. You're going to get the same kind of replacement. But look what it means in this compound. That means at this carbon you'll have OH in the front, and at the same carbon you'll have OH in the back. Are you all hearing that even if I put this on a wedge, it'll be the same two results, right? Okay. It doesn't matter. Wedge, dash, dash, wedge. Okay. Then I'll just do one more compound to demonstrate what I am talking about. Let's say over here I have a methyl group, and over here I have a Br, and I treat this with H2O. By the end of this lesson, you will know why methyl is not a leaving group, why Br is a leaving group, why the conditions here give SN1 conditions, and you will realize that racemization here means the following. That notice I put this OH in the front on this chain, and over here I put it on the back on this chain. But nothing happened here, so I'm changing nothing about that. So I'm still going to have methyl over here, and I'm changing nothing about it. I'm still going to have methyl over here. Does this fix the concept? Here's the point. Racemization only means that you're attacking both sides on the carbon that became a carbocation. So you're going to have a front attack and a back attack. But that doesn't mean you get a racemic mixture, because these are not racemic, they're the same. I cross one out. You're not supposed to draw both products. If you draw both products, you're going to get points deducted on the exam, because these are not two different products. They're the same exact thing. Turn that around. It's the same thing. That's why we had to be strong in Chapter 3, right? On the other hand, this right here, when that leaves, you get a carbocation. When that attaches from the front or back, you do get a racemic mixture. These two things are enantiomers. Enantiomers. Do you see that? And here, when this comes off and it attaches from the front or back, you get R and S at this position differences. But if there's any chiral centers elsewhere, there won't be any differences in those chiral centers. No reaction happened in those chiral centers. So these are diastereomers. Do you see how you could get the same, or enantiomers, or diastereomers? Send me the picture. I could take pictures, but I should ban pictures. The reason I should ban pictures, it's the same reason I never like doing videos, because there's this feeling of like, I'll watch it again and I'll learn it later. I'll watch it again and learn it later, that's for cycling. But when it comes to learning, we want to learn it now, watch it now. Anyway, back to this. So do we get what racemization is? Do you understand that doesn't mean a racemic mixture? That just means the carbon that got attacked racemizes the direction of the nucleophile. You get both directions of nucleophile. We're still in SN1. I haven't shown you SN2 yet. And since this breaking of the octet is the slow step, here is where we finally connect this to Chem 2 and refining what we learned about K constant, for example, rate law. How do you write a rate law for that slow step? You're going to say that the rate of this step has to do with a K constant multiplied by the concentration of the reactant Do I put anything else? No, because there's nothing else over there. What power is it? Do I have to do experiments? No, that's my mechanism, so I know that the molecularity, or the coefficient that is of the substance, is the exponent in the rate law. I know that to be true. Now, have this little thought concept with me. Go on this little thought journey with me. Let's say we have this reaction. Let me actually do this I was going to do something, but I'm going to change the idea because I think it'll be closer for all of us to understand if I do it this way. If I have a general HA plus B minus, let's say, like acid-base reaction, right? Like HA and B minus becomes A minus and HB, right? That's a general acid-base reaction. It all happens in one step. What is the rate of that reaction? It's going to be K times the concentration of your acid multiplied by the concentration of base. That's going to be the rate of the reaction. But like now go on this little journey of thought. What if I put 1 molar water and 1 molar ammonium into this flask and beaker. And in here, in this beaker, I put 1 molar hydroxide and 1 molar hydrochloric acid. Right? Notice, what's the rate, if this is an acid-base reaction, if this is an acid-base reaction, what is the rate of this? The rate is going to be a K constant multiplied by the concentration of acid multiplied by the concentration of base. But here it's 1 molar, 1 molar. So for this, the rate is going to be equal to K. Correct? Because K times 1 times 1. What about this? What will the rate here be equal to? It'll be equal to K times 1 molar times 1 molar. So it'll be equal to K. So what's your feeling on this? Do you think that both of those flat beakers are going to have the same rate? Who thinks this one is going to have a faster rate? Who thinks this one's going to have a faster rate? I'm with you. I think the much stronger acid and much stronger base is going to have some sort of a faster rate than the weaker acid and the weaker base. What that tells us is it's not concentrations that change the rate. It must be different K constants, right? So what factors influence K? Like, obviously, the bigger the value, hear me out, the bigger the numerical value of K, the faster that rate is, right? But what creates a big numerical value of K? Here's what creates it. Since in this rate law, I see a concentration of HA, K will depend on who HA is. And the better the HA, the larger the value of K. Imagine B minus was not in the rate law. Then it wouldn't matter who the hell B is for the K. But since B minus is in the rate law, K will depend on who B minus is. And if there's a C, K will depend on who C is. And if there's a D, K will depend on who D is. Keep that in mind. Do you see how that's a little bit of refinement? In Chem 2, we just say the bigger the K, the faster it goes. But now we're saying what makes a K bigger? What creates the better K? Do you see the fact that in this rate law, we have a carbon, right? So K will depend on, number one, the type of carbon. You still alive, awake, paying attention? K will depend on the type of carbon. And what kind of carbon is that? Well, you could have primary, secondary, tertiary, and so on. The best kind of carbon, actually, would be a resonating carbon. That would be better than tertiary. That would be better than secondary. And no primary for an SN1. Whoever watches this video later is going to obviously, most likely, leave comments that resonance is not better than tertiary. But we could use homolytic bond association enthalpies, heterolytic stabilities to actually see that in reality resonance wins over tertiary. Resonance wins over that kind of hyperconjugative inductive effect, even though in textbooks it says that tertiary is more important than secondary resonance. I disagree. Resonance isn't something you could see, so if you have a carbon with a leaving group, how do you know whether resonance is there? You have to make the leaving group leave and check out the carbocation that you have. And I hope you see that this won't have any resonance. This carbocation is going to be a secondary, so it's possible to do it. If you had that right there, then this carbocation is a tertiary. That's even better. And imagine over here was a double bond. Even though you don't see resonance here, it's because it doesn't have it. It's the carbocation. Does that get resonance? And do you see that you could do resonance with the carbocation? So resonance is better than tertiary, better than secondary. This could make a whole lot of sense for you if you realize that this is the rate determining step. and I had you do Hammond's postulate for a reason. If this is the rate determining step because it's an uphill step, that means going from reactants to products is going to be uphill, right? Could you all realize that if I find a way to make the carbocation more stable, that's bringing down the energy of the products, that's lowering the hill. Does that make sense? And by lowering the hill, I'm increasing the rate of the reaction. And through the Arrhenius equation, that means I have a larger K. You might want to revisit the Arrhenius equation. Activation energy. You know, it was illegal in some college or some other college. So the type of carbon, look what I'm saying. Look what I'm saying here. Since you see some substance, then K depends on its identity. For example, you see the carbon in here, so it depends on what groups are attached to the carbon. And also, there's a leaving group, so it depends on how much the leaving group wants to leave. So the next thing that it depends on is the type of leaving group. The better the leaving group, the faster it'll leave. Look, isn't that true over here? Watch this, watch this. If this breaks apart and I find a way to lower the energy of the carbocation, it's easier to climb that hill. But if I lower the energy of the leaving group, it's also helping me climb that hill. Do you see that's lowering the energy of the products, helping me climb the hill? So the better the leaving group, well, what's a good or bad? Better at leaving. And if something is better at leaving and taking electrons with it, who is going to leave and take electrons and become negative? Somebody that's stable with those electrons and becoming negative, right? Wouldn't you say that that's a very negligible base if it's a good leaving group? Because you want it low in energy? And what it is a base? So you want a low energy base that's a negligible base? If this is a high energy base like hydroxide, it's not happening. But if it's a low energy base like chloride, it's happening because chloride is the conjugate of a strong acid HCl. Doesn't that make sense to us? We'll refine in this lesson what the leaving group is supposed to be. But I'm just saying the better the leaving group, the faster the rate of the reaction. And then the real question is, how the hell does it leave all by itself? Like anybody reading the chapters, like how could it possibly leave all by itself? There's one more thing we see in this rate law. Not only do we see a carbon in here in a leaving group, we see brackets, and a bracket indicates solvent. And number 3 is the type of solvent. And that, by the way, is the major secret here. That's what causes the bond to break. The polar protic solvent. I've already had at least one student email me and ask me, Professor, why is hydroxide a bad nucleophile? I thought you said that a nucleophile is a base. And number 1, hydroxide's not a bad nucleophile. But if you look at this table of nucleophiles, did anybody look at the table? There's a table of nucleophiles. Good nucleophiles, bad nucleophiles. Raise your hand if you look at that table. It's saying something other than you think. And unfortunately, that table, what it's trying to teach you, not only are you not learning, but in many cases, your professors are not learning it. So I don't know about any one particular's recitation or instructor or lecturer, but after this lesson, I hope you're going to see what that table's actually trying to inform you. See, when it comes to acidity and basicity, it's easy to say this base is stronger and that base is weaker, and this base is stronger and that base is weaker, because we judge them based on pKa, and for pKa, we always put it in water. But when it comes to nucleophilicity, because the solvents can vary in different environments, a stronger base might behave weaker, or a weaker base might behave stronger, because you're changing the environment. And for that reason, we don't even use the word base anymore. We use nucleophile, because base means it should be in water, and nucleophile is like a base in different systems, in different areas. So what we want here is a polar protic solvent. Let me connect this to something we learned. There was this lesson I did over the weekend. Some of you were here, that we talked about ion-ion and ion-dipole and dipole-dipole. And that had to do with this equation, Coulomb's law. F is KQ1 Q2 over R squared. What I also mentioned was there was an epsilon value here, but we leave it out because in air the epsilon is about 1. So the epsilon value of air is approximately 1. It's like 1.03 or something like that. So if I put the number 1 here, or I don't put anything at all, it's still the same exact thing. But it turns out that in toluene, the value of epsilon is approximately 2. What's toluene? Some of you might have seen it before. It's a benzene ring with a methyl group. So somehow the dielectric constant is 2. In diethyl ether, Et2O, the value of epsilon is 4.7. Should you write these numbers down? Right? Because I'm putting something on the board that is completely meaningless, right? I memorize numbers that I don't want my students to know because I like to fill my head with absolute bullshit. Meaningless chitter chatter. If I know it, I expect you to know it. Once this course is done, if I put it on my board, I expect it in your head. That's where I expect it. Big expectations. Dielectric constant of air is this. Toluene is that. Diethyl ether is... what does this mean? It means an oxygen with an ethyl and an ethyl. Diethyl ether. Right? After that, CH2, Cl2. That's about a 9. After this is acetone. That's about a 20. Listen, it's not even close to a complete list. I'm giving you a short list over here. I want you to at least know this list. And you will see. On our next lesson, we're going to expand on what this is about. But I hope you're already seeing the power of knowing pKa values. I hope you're already seeing, like, in substitutions and so on, you could figure out which is a stronger or weaker. And just wait until it gets better. So acetone's at 20. Ethanol, ETOH, is around 35. I don't have any room, but underneath there, right, methanol, which is a, I think I messed up. Ethanol is around a 25. Methanol is around a 35. I might be off on that. We have to verify that. You could look that up. Not now. Later. See who's first to email me, and it's a long day and my brain's not exactly computing. For some reason it feels wrong, but I'm fairly certain methanol's a 35, so ethanol can't be that much. It's somewhere in that range. And then water, can't get water wrong because, well, that's biochem. That's an 80. So here's the way to think about this. There is a force of attraction between Na plus and Cl minus. You have table salt. You spill it out, right? Na and Cl are stuck together. They're attached, right? How do you detach them? Put it in water, right? Put it in water. Or you heat them up because you can add heat. Heat breaks a bond. Endothermic to break a bond. Exothermic to make a bond. But why would water break them apart? It's kind of different than what you think. It isn't because, oh, you get better bonds. That's not true. The bonds here are ion-ion. And the bonds here are ion-dipole. That's actually worse bonds. Ion-ion, ion-dipole, that's worse bonds. It's an entropy reason. You've got one thing that breaks apart in two. So going over here, this way is entropy. Going over there, that way is enthalpy. And together, they're two stuck on each other. And if you could kind of weaken their stickiness, then entropy will take over. How do you weaken their stickiness? Here's the point. There's a force of attraction between them, and that force has to do with their charges, their distance, and an epsilon value. The force of attraction is some amount. We don't even have to talk about what the number is. Just imagine they're very, very stuck together in air. How stuck are they in water? I'm just comparing air to water. You could have a number here. In air, you put the number 1 over here. So this is how stuck they are in air. Now, whatever that number is, you put it in water, and you're putting an 80 in the denominator. They're 80 times less stuck to each other when you put them in water, right? Yeah. Water happens to be a polar protic solvent. In fact, your polar protic solvents are going to be water, alcohol, or a carboxylic acid. Those are, if there's anything that's not on that list that's a polar protic solvent, then it's a small chance you're going to see that. Basically, anything that has an OH hydrogen bond donor is a polar protic solvent. But the word protic, can you remember the word protic indicates some kind of acid idea? So either it's water, like not an acid or a base. Are you hearing me? I'm about to refine something, so I need you to pay attention. What was the question that you just...
Sorry, I was asking if that's
RCOOH or RCO2H, a carboxylic acid. So you have water, an alcohol, or an acid. Proton, acid, H+, acid. It's either neutral, not an acid or a base, or it's an acid. It has to do with ROH. Do you see that's a partial positive H? That's like the polar protic part. So some students see ROH, and then in an exam question they see KOH, and they're like, polar protic solvent. That's a strong base. That's the opposite of a protic anything. That's a hydroxic something. Could you tell that that's K plus OH minus? That doesn't count at all. That's not a polar protic solvent. Okay. We're almost there. I just need you to complete a thought with me. If NaCl fall apart in water, then why won't RCl fall apart in water? Do you see that dissociation? RCl can dissociate because the solvent can weaken the attraction between them, creating a solvent shell around this, and it's the entropy of them falling apart that guides this, that determines this. And the greater dielectric constant that you have weakens the force of attraction because that dielectric constant is in the denominator. Do you see? It's a real simple overall idea that if you don't have that idea in your head, you're going to be stuck and say, how did the leaving group just fall off? It didn't just fall off in the air, just like Na and Cl didn't just fall apart in the air. If you put it in the right environment and the right solvent system, the solvent helps them separate. It's called solvolysis. And you need water, alcohol, or a carboxylic acid. So to me, the most important thing that drives the rate of an SN1 reaction is the solvent. Of course you need a leaving group, and of course you need a carbon that helps you do this, right? But if I had a compound like this with a leaving group on a tertiary position, and I even had some nucleophile, it's not going to go SN1 unless I have the correct solvent to enable the dissociation. Just like ions dissociate in water or in alcohol, I need water or alcohol. I need something like that to help this dissociate before something can attach. Do you see what drives? The bond breaks because of the solvent. That's what causes the bond to break. I hope you also, in the back of your mind, are seeing that this is just a way to extend what we know from chapter 14, which was rates of reactions in Chem 2. I don't know what chapter it was in any other book, but rate is equal to K times concentrations. Do you see how now we're like not just saying, okay, K is a number, like 1 times 10 to the 4th. We're now saying what that number depends on. You'll have bigger numbers when you have better of these things. Now, what if you have a good or bad nuke? Does that matter for the rate of an SN1? You don't see a nuke in the rate law, so K has no bearing on how good or bad the nuke is. Put a great nuke, won't change K. Put a bad nuke, won't change K. Do you see what I'm saying? If I take away the nuke or add the nuke, it doesn't matter. I'm still going to have the same rate of the reaction over here. If I change the solvent to an alcohol, I change the dielectric constant, I'm going to have a different rate. Do you see? Compare that to SN2. Now on this side of the board, I'm going to write SN2. I know this lesson is extending, but do you want to learn this or not? It's 10:09. Trust me, I'd like to go home and grade about 200 exams. No, I wouldn't like to do any of these things, but I would like to go home, but I still have to grade the exams. For SN2, it's a little bit different. Some ideas in here are different. For example, you still have R, R prime, R double prime, but this time I'm actually showing the tetrahedral arrangement. Here I don't show the tetrahedral arrangement. Because in SN2, you've got a bonding orbital, and on the other side you have an anti-bonding orbital, and the nucleophile will put electrons into the anti-bonding orbital, break off the leaving group, and it'll flip over. Do you see I have to flip it over? If I don't move any of those R groups, if I just release the leaving group and attach the nucleophile, do you see it'll look a little weird if I draw it like this? So this bond shifts over to this side. The wedge stays in front but goes to the other side. The dash stays in front but goes to the other side. It pops over. It's like taking a hat and flipping it inside out. You see that? It's called inversion. Inversion of stereochemical configuration. R, R prime, R double prime, and you have a leaving group minus. It's not always going to be a negative nucleophile. Just like over here, it's not always going to be a negative nucleophile, but it's going to be a base, and the leaving group's a base, the nuc's a base, and the leaving group's a base. So what separates them? The nuc should probably be a stronger base because it wants to attack, and the leaving group should be a weaker base because it wants to fall off. Now a base, you realize, can be either negative or neutral, so sometimes you're going to have neutral bases. This is called inversion of stereochemical configuration, and as you read the chapter, you're going to think this is true. You're going to think that if this starts out as R, when that attacks, it goes the other way, so it becomes S. That's true in many, many, many cases. But just like racemization over here didn't mean that your products are a racemic mixture, inversion does not mean you get R from S or S from R. Here, if you started with S, you get both R and S. If you started with nothing, you get nothing. And if you started with a molecule with multiple chiral centers, you get diastereomers. Right? Here, what if R, R, and R are the same? So it inverts, but you don't get any RS from here. And a lot of times, if this is R and it inverts, it gets S. But sometimes if it's R, it stays R. So what's the confusion there? There shouldn't be any confusion. Nobody says inversion means the letter R changes to the letter S. It just means that the nuc comes in from a different side compared to where the leaving group is. If the leaving group's in front, the nuc comes in from the back. If the leaving group's on your right, then the leaving group's on your left, right? I have to double check because this is my right. Anyway, how could that be? If this is R, how come this doesn't invert and become S? Because it depends on who the leaving group, who the nuc, and what these are. Let's say this is R because the leaving group is number 1, the double prime is number 2, and this one is number 3, and that's the lowest priority group. When a nucleophile attaches, who says the nucleophile is now number 1? What if the nucleophile is just some other carbon? It's not number 1. What if something else is number 1? So this could be R, and then when a nuc attaches, now you have a different number 1, and it could still be R. All it means is that if the leaving group is here, the nuc is going to be there. If the leaving group is here, the nuc is going to be there. Inverted compared to where it was. Sort of like an inversion center. The opposite direction compared to where it was. And since this is all happening at once, what is the rate law of this? The rate is equal to K times the concentrations of both of the things that you see, which is going to be carbon, leaving group, R, 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 R prime, R double prime, and nuc. Suddenly nuc gets its day, right? Nuc makes a presence. K, of course, depends on several factors. Here it's 4 factors. Why 4? Well, you see a carbon in the rate law. Therefore, K really matters what carbon's attached to, type of carbon. And what we want here is very much different than what we want over there. Over there, the best kind of carbon is the most stable carbon, like resonating or tertiary. We're not looking for stable carbocation because here you don't make a carbocation. If it's really purely SN2, there's no carbocation quality at the transition state, and the book really, really botches the transition state. I didn't mention this in yesterday's lesson, but if this is really a nucleophilic substitution, and this is really a single arrow going in the forward direction, then this is a downhill reaction. And if it's a downhill reaction, the activation energy is closer to the reactants than it is to the products. There's not going to be the same amount of bond breaking and make a pentavalent intermediate. That's not possible. There is no intermediate. It's a transition state, and it's not pentavalent either. It looks more like reactant than product. Could you understand that since it's going downhill? Because there's 2 things at the reactant and 2 things at the product. There's the same amount of entropy, and there's only an enthalpy possible change. We'll talk about this. Type of carbon. You know what you need over here is the room for the nucleophile to go and attach. And I said this in the video, if these are 3 carbons, there's no room, unless this is a bigger atom than carbon, like if that's a silicon. But since we're dealing with carbon, if you have all 3 hydrogens, then that's a methyl carbon, and that is the best kind of carbon. Carbon with 3 hydrogens, that's a methyl with a leaving group. That's the best kind of carbon because you could attach to it. A little worse than that is primary. That means one of those are an actual R group. Worse than that by a good amount is secondary, and tertiary, no deal. So if you see that your carbon with leaving group is a tertiary, it can't do SN2, but it could do SN1. That doesn't mean it'll go SN1. What if there's no polar protic solvent? If there's no polar protic solvent, you're not getting SN1 no matter what. See, what is the driving force of SN1? It's not just falling off, it's the solvent enables it to fall off. What's the driving force of SN2? The answer is the nuke that breaks this bond. Yes, we need a particular solvent here, but the solvent doesn't matter too much. That's, by the way, that table of nucleophiles where they call it a good nuke and a bad nuke. Those are not really good nukes and bad nukes. You're going to see they're putting the nukes in the wrong solvent conditions to teach you that sometimes a better, stronger base might get distracted by the solvent a little bit better and become a slightly worse nuke. So nucleophilicity depends on solvent. We'll deal with that. But if I have the wrong solvent, this reaction won't happen. And if I have the wrong solvent, this could still happen. If I don't have a nuke, doesn't matter what solvent I have, this reaction won't happen because the nuke causes the bond breaking. Do you see? To me, the most important thing on this board right here is the nuke. And the most important thing on this board right here is the solvent. Assuming you have a carbon and a leaving group, you know what I mean? Like you don't have a carbon and a leaving group, there's nothing to talk about. But let's say you have a carbon that's secondary and a proper leaving group. Then it could be SN1 or SN2. Right? And the only determining factor there is there a nuke that really could do it? Then it's SN2. Or is there a solvent that's polar protic? Then it's SN1. Type of carbon. And resonance here doesn't matter because you're not making a carbocation. Type of leaving group. Obviously, the better leaving group, the faster this reaction is, more stable leaving group. Type of nuke. Now, I can't just write what kind of type of nuke we need over here. We're going to have to investigate different nukes that are possible. And the last thing here is the solvent, which we need a polar solvent to dissolve the various ions, but it needs to be aprotic, not protic. I'll give you a little hint on this to understand that table. If you read that table of like good nuke, bad nuke, because how could I minus be a great nuke when it's the most stable base? I minus is the most negligible base, and then OH minus is a worse nuke. Isn't a nuke a base? Imagine we have a methyl with a leaving group, and I have F minus, and I have OH minus. That's so much stronger of a base. That's so much stronger of a nuke. It's going to want to attack and kick that off. But imagine, instead of SN2, I put in the wrong solvent. Instead of an aprotic solvent, I put in a protic solvent. Imagine I put this whole thing into acetic acid. Didn't I say already that the way we're going to think about orgo is to think about reactions in the way I taught them to you? So the first reactions we ever learned was acid-base, and now we're learning substitution. Before a substitution can happen, if there's a chance for acid-base, it's going to do acid-base. So my point is the protic solvent is an acid, and we have a stronger base and a weaker base. What's going to happen is the better nuke will just deprotonate the base, and this one, deprotonate the acid, and this one will be like, okay, I have nothing else to do. I might as well do a substitution. If there was no acid, the strongest base would be the strongest nuke. But if you put it in a protic solvent, you distract the strongest nuke, and whoever's left over wins the race. Does that make some sort of sense? Let's say you have two runners, right? The world's fastest runner and the world's second fastest runner. And this one just happens to be very hungry, and this one ate. And as they're running, there's a cheeseburger thrown. The world's fastest runner goes that way, and the second fastest wins the race. That makes some sort of sense? You put it in a protic solvent, protic means acidic, and suddenly the best nuke gets distracted the most. Right? So now what if you just had a nuke and a leaving group and you put it in the wrong solvent? It'll slow down the reaction a little bit. You're distracting the nuke a little bit. It'll still have the reaction. Without a nuke, you won't have any reaction here, right? So we want to investigate who's a nuke that's good enough to do SN2. And we also want to investigate who's leaving groups that are good enough to do both SN1 and SN2. And why I left that on the board is I want you to notice one thing about a leaving group. We're not far away from being done, by the way. I want you to notice one thing about a leaving group. Whether it's an SN1 and the leaving group leaves, or SN2 and the leaving group leaves, do you notice that it leaves in the same exact way? And not in time. Obviously, this leaves first, and that leaves at the same time. But it leaves in the same way. It takes electrons with it. It takes electrons with it. It's connected to a carbon, and it steals all the electrons out of that bond. Does everybody see that arrow push? Yeah. I need you to keep that in mind for the next screen. So we have two things to learn right now. What kind of leaving groups there are, what type of nucleophiles. Where does the nucleophile matter again? SN2. It doesn't matter for SN1. I'll say one more hint about that table. For anyone that knows the table I'm talking about, the table of good nuke, moderate nuke, weak nuke, read the title of that table. Almost no professor reads it. That's the even crazier part. On the title of that table, it says nucleophilicity and their relative strength in water or methanol. Or water, sorry, or alcohol. Is that the right solvent to be considering nucleophilicities? Aren't those solvents polar protic solvents, not polar aprotic solvents? So that table's not actually teaching you what's the strong nuke and what's not the strong nuke. It's what happens to the strongest bases when they get put into a confused solvent. You hear what I'm saying? Yeah. Put it in the wrong solvent and the strongest is no longer even in the room anymore. He leaves, she leaves. And whoever's left over is the nuke. That's the idea. I'm not even gonna address what various professors in various schools are going to question you on, right? Because since many of them didn't read the title of the table, to them it means I minus is the stronger nuke than OH minus in like all cases or something like that. What I will once again ask you all is to put the right answer on the exam, regardless of what answer you think the professor might want from you. Because the professor could change their mind on what they think the answer is to the actual correct answer, has happened many, many times over the years, many times over decades. So anyway. And I'm absolutely not talking about any single professor. The professor that I'm mentioning most is a professor that I actually had who said this in class, but on the exam it seemed different. It's like, but you said, no, I didn't. You heard me wrong. There was no videotape evidence to prove anything, so. Not going to have enough room for all this. Were there electrons there or not? Great, now I have to draw the Lewis structure. There may be electrons here. I don't remember. I have a very bad memory when it comes to memorizing pictures. I have a good memory when it comes to various things, but I have a bad memory when it comes to memorizing things like Lewis structures, because I could always draw them, so my brain said, why memorize it? I could draw it, but There may be a set of electrons here. Go back to lecture number 1. What is this? What is this portion right here? ClO3 minus, right? If I break that off, it's ClO. That was the first lecture? Here, in this room. I'm going to show you one more over here. O, S, double bond O. I'm leaving proof, by the way, that Orgo and all these different classes that they're not to be memorized. I remember certain things, but I definitely didn't memorize all of it. I could make so many mistakes, like trying to come up with the integrated first order rate law. I remember there's logs in there, but I don't remember exactly how the rate law goes, even though it's easy for other people. I could derive it in about 1.5 minutes. So to me, it's you have to remember how to get there, and then you could always get there. Every time I draw cholesterol, I don't memorize it. I use a set of patterns to remember how to remember it, but it's not. I can't immediately tell you the difference between two cholesterol pictures at all. I just know it's a tetracyclic ring system, so I start there. I know it's a transdecalan, so I go there. So what do I want you to do? Name this. No, I'm kidding. I'm kidding. This is some sort of a chain with a bunch of potential leaving groups, right? And I just want you to analyze this with me for a few minutes. We're done relatively soon. There's just one thing I have to show you after this, which is the nucleophiles, and then we're done. I know that today's a late day, but you know you're going to appreciate it, hopefully, when you do well in the next exam. So, how does a leaving group leave again? It takes the electrons with it. I said whether it's SN1 or SN2, it leaves by taking the electrons from the bond. So if this is the leaving group, it's going to take electrons with it. If this is the leaving group, let's remember this has 2 electrons. Do you know that? Because it's supposed to have, this has 6, this has none, this has that, this has this has this has none, this has this I already put the electrons in. It's really bothering me whether there's electrons there or not. Seven plus 6, 12, 18 plus 1, 19, that's 26. Minus 6, so there's 20, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. It's not bothering me anymore. See, I tried, I worked it out. Chemists try. Yeah, because you have a bond this way and a bond that way. Yeah. So it's that. So this leaves like this leaves like that 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 would leave like that, and this would leave like this. And that doesn't mean these are all leaving groups. We're about to analyze whether they're leaving groups. Are they going to leave? And it turns out that a leaving group must leave as something stable. Stable. Not stabilized. That's the wrong thing, because resonance could stabilize. I'm talking about stable. And we defined something stable. Something that was a stable thing was negligible. For example, a stable acid is a negligible acid, and a stable base is a negligible base. And since these are leaving with their electrons, they're leaving as a base. We want a negligible base. What's a negligible base? Something that has a conjugate acid that is a strong acid, which is water's conjugate acid, H3O plus, or stronger. Do you realize, like, I had the cutoff? I had H3O plus and HCl and HBr and HI. All of the conjugates there were negligible. So anything that leaves as negligible, meaning if I'm checking if this is negligible, the conjugate has to be a 0 or a -5. If the conjugate is like a 2, 3, 4, 5, 6, that's not leaving. A 2 is going to be difficult to leave. The conjugate, a base that has a conjugate of a 2 is going to be difficult to leave. A base that has a conjugate of a 7 is going to be even more difficult to leave. Like, I should put one more in here. And this leaves like that, right? So would this leave? If this leaves, it's going to be NH2 minus. What is the conjugate of NH2 minus? Everyone should know it's NH3. And NH3 is a 38. And that's a whole distance away from a 0. Do you see? There's no freaking chance NH2 minus. This is Avogadro's number of marshmallows. This is the world of marshmallows falling on your head. That's not leaving at all. No chance. How about this? Is there any chance that this leaves? When that leaves as F minus. F minus has a conjugate of HF, which is a 3. It's not leaving because it needs to be stable, and this is less stable by 1,000 times. Do you see that? This is less stable than that by 1,000 times, but that's infinitely more stable than this, right? So if I say this is not leaving, it's staying, then this I have to just like... If I had a bazooka, I'd blast a hole through the wall over here to emphasize exactly what I'm talking about. There's no way that's leaving. How about that? I would use 2 bazookas. Because CH3 minus is the strongest base we could think of since that's the conjugate of a 50. That's not leaving. OH minus, is that leaving? No chance, because OH minus is the conjugate of a 16. That's not leaving. Cl minus, is that leaving? Yup. Br minus, is that leaving? Yes. We got this positively charged thing, so when it falls off, it's NH3. Now, you already know NH3 is a base, so that's not stable, right? What's the conjugate of NH3? NH4 plus. Do you see why I needed you to know about how to deal with conjugates in Chapter 4? Because now we need to just use them. It's part of our language, and if you didn't work out Chapter 4 like I wanted to, you're going to be stuck here, and just extrapolate that. If you're stuck here, you're going to be stuck in Chapter 6. Then all of Orgo 2 is going to suck. You got to start working. You got to start working so tomorrow's easier. That's what you got to do. If you're going to do that, you're going to love Orgo 2. You're going to even love Biochem more. When that leaves, that's that. And that has a conjugate that's a 9. And it's not a 0 or less. That's not leaving. How about this? Is this leaving? Yes, absolutely. I minus is leaving. Is that leaving? Is an oxygen with 2 hydrogens and a positive charge. When that leaves, it leaves as OH2, which is H2O. Water is the definition of negligible. I have it circled here. It's the definition of negligible. Of course, this thing is leaving. How about this one right here? Is this leaving? If that leaves, this leaves as, thank you so much for saying that, it leaves as acetate. And the conjugate of acetate is acetic acid. And acetic acid's a 4 to 5. And a 4 to 5 base is not as terrible as what a 9 would give me, or a 16, or a 50, but a 4 to 5 is still not going to leave, so that's not leaving. Would this leave? Would this leave? Yes, it leaves. We don't have a pKa, so how would you know it leaves? What does it leave as? It leaves as ClO3 minus. And you should know that as one of the conjugate bases of one of the 7 strong acids, HClO3. Day 1, I had you do an assignment to know this. Is anybody here? Raise your hand if you know what I'm talking about. How about you learn the 7 strong acids? Here's something to think about. If an O leaves and gets a negative charge, it's not stable enough. I said this on the first day also, so instead of being nervous, hear me now and remember it. If an O leaves, it's not stable enough because that's the conjugate of a 16. If an O leaves and it's got resonance stabilization, but just one amount of resonance stabilization, see, like one extra contributor, it's not a 16. It's not a 16. It's 10 units less. It's like a 5, but that's still not good enough, right? So an O minus won't leave. A half an O minus won't leave. But if you have 3 resonance contributors, do you see you're going to get 3 resonance contributors? Then that's not just minus 10, but it's minus 10 and minus another 10. Do you see that? And that would put that into strong acid category. In fact, the same reasoning is over here. Because you'll get an O minus resonating to an O minus resonating to an O minus. That's 3 contributors of O minus. You get an O minus resonating to an O minus resonating to an O minus. Do you see that's 3 contributors? No contributors, and that's a 16. 2 contributors, that's a 5. So 3 contributors puts it into negative territory. Could you make sense of that? Do I have to draw it here? Here, that's a 16. So if I do this, then that's a 10 units less. Let's just call it a 6. I know it's not a 6, but 10 units less. So can you imagine if I did this? Then it would be 10 units more or less. Another 10 units less would be like a negative 4, right? And then you'd say, but you can't break the octet rule for carbon. I agree, you can't break the octet rule for carbon. That's why you always have like a sulfur over here or a chlorine over here. Do you see how you have that? Resonance is an important deal. Now, if I erase all of the stuff that are not leaving groups, and I also erase all of the stuff that are usually leaving groups in Orgo 2, you're left with those that are the usual leaving groups in Orgo 1. So it's really not difficult to remember the conjugate bases of the 3 simple Cl minus, Br minus, and I minus. Do you hear me? You know, you really need to know about resonance. So before I tell you about a nucleophile, I want to prove to you that resonance, in the way that I taught it to you, is important. We started this lesson talking about acid-base, right? Yes? And one of the things that I showed you was multiple protonation sites. And we were talking about resonance, and the idea that if I had a carbonyl over here versus an OH over here, you're not going to protonate this carbonyl because the resonance you're getting out of it isn't great. But if you had an oxygen right here, then the resonance you get out of that is great. And it's really about not how many resonance pictures you could draw, but it's about how valuable the contributors are. So here's one example that can prove that to you. One single example. If this dissociates, it makes H plus and acetate. If this dissociates, it makes H plus and phenoxide. If you draw the resonance contributors of this, you will get one additional resonance contributor. I hope you realize how. You bring these electrons here, you push those electrons up there. If you draw the resonance contributors from here, please follow this with me. Any one of these lone pairs come down and this goes to here. ABC, remember? Then this goes over here, that goes over here, then that goes over here, that goes over there, that goes over there, that goes over there. You have plus 4 more resonance contributors. I'm going to draw one of them. Bring these electrons here, bring this over here. So you have, here's one of those resonance contributors. And then I could write plus 3 more. Resonance stabilizes, right? So the one with most resonance should be the most stable base. And that should come from the strongest acid, because the most stable base is the weakest base coming from the strongest acid. Which one is the strongest acid? Let's go back and ask this. Which one is the most resonance stabilized? The answer is that one. And that's why this is the strongest acid. Yeah, let me repeat everything that I've said. The number of resonance pictures you see is not what's important. If I gave her 5 bills of money and I gave him 2 bills of money, who did I give more money? Do you know what bills I've given? If I gave her 500s and him 2 singles, she has more money. If I gave her 5 singles and him 2 20s, he's got more money, right? Here, when you resonate this, one contributor is an O minus, and the next contributor is an O minus, equal major contributors. Here, when you resonate this, one contributor is an O minus, and the next contributor is a carbon minus. Nowhere near as good as a contributor as this. And I can prove that 5 resonance is not as good as 2 resonance when it's 2 important contributors and 1 important and other garbage contributors, because the pKa of a carboxylic acid is 4 to 5, while the pK of a phenol is 10. This is the weaker acid. Do you see? The number doesn't lie. This is the weaker acid, so the conjugate's a stronger base. It's stronger, more unstable, even though it has more resonance pictures. What are you supposed to learn from this example? That it's not the number of resonance pictures, it's the number of major contributors. 2 major contributors versus 1 major contributor. What has more resonance? That does. What has more pictures? Who cares about pictures? It's what has more major contributors, more resonance. You know, the word contributor is amazing because, like, let's say I wanted to start a company. And I had 20 people that contributed money to me starting the company. Who cares if they all give me 50 cents each? Like, they're worth it. Thank you for contributing money. But all I need is that one donor to give me $1 million, and I'm good with starting the company, rather than 100 people that give me $5 each. You know what I'm saying? Like, that's great. It's nice, but it's not about nice. I will be able to start a company faster with $1 million than with, it's the major donors, the major contributors. We learned what a leaving group is, right? Now we need to learn what a nucleophile is, and what reaction does the nucleophile matter? SN2. So I'm not trying to find what a nucleophile is. I'm just trying to find what a nucleophile that can do SN2 is. Nuc for SN2. This is the last thing I put on the board. We're going to get some rules, show you how to use this in examples for homework, and then you do homework examples. A nuc for SN2 is one of 2 things. Do you remember when I taught you what chiral means? It means it doesn't have a mirror plane or an inversion center. It's either or. It's the same thing with a nuc for SN2. There's an either or. It could either have one quality, it's a nuc for SN2, and if it doesn't have that, it could have a different quality and it could be a nuc for SN2. It doesn't have to have both. If it has both, great. If it doesn't have either, it's not a nuc for SN2. The first thing is really easy. If it has a non-resonating negative charge. What does that mean? I didn't say, so years ago I used to write if it has a negative charge, but that's not enough. If it has a negative charge, that's localized. For example, this meets the criteria, this no longer meets the criteria. That negative charge has resonance. So that doesn't mean it's not a nuc for SN2. It could still be a nuc for SN2. We just need to check the second thing. Right now, it's not a nuc for SN2 because of the first criteria. If I didn't have this, it doesn't have to check anything. It's automatically a nuc for SN2. Do you see this? What's the second thing? The second thing, and this is or, could be either. It could have both. It has at least very weak basicity. And this line right here, wow, I need to go to sleep. Basicity. This line right here is the reason we learned chapter 4. Because if it's a very weak base, or a weak base, or a moderate base, or a stronger base, or a strong base, or a very strong base, we need to know some pKa to support that. So what I'm saying is, another way to look at that is, the thing that's a very weak base, I'm not saying it has to be a very weak base. It has to be at least a very weak base. Now what's less than a very weak base? A negligible base, meaning it can't be a negligible base. So if it has no negative charge, or if the negative charge is resonating, and it's a negligible base, it's not going to be a nuc for SN2. Is Cl minus a nuc for SN2? Well, it's a negligible base, but it's got a negative charge, automatically a nuc for SN2. Is this automatically a nuc for SN2? We have to check basicity. Because since it's resonating, we have to check basicity. Is this a nuc for SN2? We have to check basicity. There's no negative charge. No negative charge, we need to check basicity. Is this a nuc for SN2? It can't be a nuc for SN2. It's not a base, it's an acid. There's no basicity. There's no negative charge. Do you see? So to be a very weak base or more, it has a conjugate acid with pKa greater than or equal to 1. Is that an easy enough criteria? If you know your pKa table, then you could figure that out. Is this a nuke for SN2? It's got a resonating negative charge, so we have to check basicity. What is the conjugate acid? Conjugate acid here is acetic acid. What's its pK? 4.8. Is 4.8 bigger than or equal to 1? Yes. So the conjugate over here is a good enough nuke for SN2. Here's a bunch of random things on the board. I want to circle all of the ones that meet the criteria for a nucleophile for SN2. Circle all of the nucleophiles for SN2. You have 10 seconds. Sorry that this lesson is over an hour over. Time flies when you're having misery. But you live longer. Because time flies when you're having fun. So we shouldn't have any fun. You live longer. Here's something we could do automatically, right? So you realize, whatever, I'll put in the dots, didn't really matter. Do you notice that that's a negative charge, no resonance? So is that. And so is that. So definitely those are nukes for SN2. I don't have to check basicity if there is a negative charge that's stuck without resonance. It's either that or that. Automatically, I pick the ones that are negative and not doing resonance. If this was on here, I would look for basicity because there's resonance there. I'm not automatically circling it, right? Okay. Now I'm going to look at which ones are a base. Is that a base? Yes. But isn't everything a base? Isn't water a base? Isn't water the conjugate base? No, the water's a conjugate base of a strong acid. It's negligible. The conjugate of this is 0. 0 is less than 1. Conjugate of this is 4. 4 is bigger than 1. This works. What's the conjugate of that? I don't know. I don't know. We don't have this number, right? But when in doubt, I'm going to replace an R group with a hydrogen, and this is water. So, and water doesn't work. I don't have the conjugate acid of this because it's an acid. So what do you think? Do you think an acid is a base? Yeah, I don't think an acid's a base either. I don't think a duck is a pen, a car is not a tornado. Different things are different things, and an acid is not a base, so I'm not going to circle it. Now that's a base, you should have learned that from Chem 2, but if you didn't learn that from Chem 2, the conjugate of this is a 9, and a 9 is bigger than a 1, so I'm circling that. This just doesn't have any electrons, so forget that. They're all sigma bonds. And this doesn't have any electrons, it's a cation, right? Forget that. So besides the crap that I threw in here just as randoms, right? Do you notice what didn't qualify as a nucleophile for SN2? What didn't I circle? What didn't qualify as a nuke for SN2? A polar protic solvent. A polar protic solvent cannot be the nuke for SN2. Do you see a carboxylic acid, a water, or an alcohol? Here's what I need you to do. Here's the homework assignment. I want you to do every question you can from the back of the chapter, go to other chapters, because we're not going to answer the question. We're going to do something else. We're not going to answer the question. We're going to do something else. I don't want you to tell me what the products are. I don't want you to tell me what the stereochem is. Nothing like that yet. The very first thing I need you to know is, does it go SN1? Does it go SN2? And the answer is, it could be going SN1 and SN2. It could be going neither. So how do you find that out? Think about everything we've learned today. Put it all together right now. Number one, to be SN1 or SN2, there must be a leaving group. In both cases, there's got to be a leaving group. So do you see any of those leaving groups connected to a carbon? Now, sometimes you'll see it here. Sometimes you'll see it over the arrow. It doesn't matter. Student asked me about this and was really confused. There's nothing to be confused about. We put things over and under the arrow to save space. So if this was Chem 2, we would just write this plus NaSCH3 plus DMSO and then an arrow. Don't look too deeply into what's above, below the arrow at all. It's just this, this, and that are all in the same flask. Is there a leaving group on any one of these things? It has to be a carbon that's sp3 that has a bromine, chlorine, or iodine at least to begin with. Could have some other things on there, but there would have to be one of those crazy things that I showed you, right? There is. This is the carbon with the leaving group, right? So we're going to say, is there a carbon with a leaving group? The answer is check, right? Now we want to know what type of carbon that is. What type of carbon is that? Well, it is a sp3, but in terms of primary, secondary, tertiary, all that, this is a secondary carbon, right? And you don't have to have the notes from today hidden somewhere. You could have what K depends on for SN1 and SN2 in front of you as you're doing this. You'll remember that SN1 could happen on a secondary and SN2 could happen on the secondary. So over here, I'm going to do this and write SN1 and SN2. Both of these are possible. Do you see my map? Both of these are possible. Like if I don't have a carbon with a leaving group, no reaction. At least not SN1 or SN2. And if I have a carbon with a leaving group, let's say it was tertiary, that means SN2 is not possible, I could only do SN1. And let's say it was primary, SN1 is not possible, I could only do SN2. What was the most important thing for SN1? Polar protic solvent. So I've got to look for water, alcohol, or carboxylic acid in here. That's not water, alcohol, or carboxylic acid. That's not water, alcohol, or carboxylic acid. And whatever DIMSO is, it's not water, alcohol, or carboxylic acid. If it looks exotic, think it's a polar A protic solvent or something like that. Or go ahead and memorize 100,000 different polar A protic solvents. And the second you think you memorized everything, on an exam it'll say dioxane. You'll be like, the hell is that? I've never seen that one. So if it looks like something exotic, it's not it. The problem is we don't have a polar protic solvent here. There's no water, alcohol, or anything like that. We go like this. We go solvent, and we cross that out. So we cross that out. SN1 is not possible. Does that mean it automatically goes SN2? No. What was the thing that was important for SN2? We need a nuke. Now, is there a nuke? Now, this is where we have to be a little careful. We have to remember some Chem 1, Chem 2. Here is a compound. And when you see a metal connected to a nonmetal, do you see that's a metal connected to a nonmetal? You have to automatically, in your mind, realize you're looking at Na plus and SCH3 minus. Do you see that's an ionic bond? So whenever you see an Na or an Li or a K connected to something from this side, you automatically break it up into this and then ask yourself, is there a nuke for SN2? Some of you are not listening close enough, so when you go home, you're going to be like, I don't get it. He said water's not a nuke, but it's doing SN1. It's not a nuke for SN2. It could be a nuke for SN1 because it's got electrons, and when a carbocation is there, it can attach to the carbocation. That wasn't the criteria. We were asking about what could be a nuke for SN2, what could backside attack with enough strength to break the bond to a leaving group. Do you hear what I'm saying? So does this have the nuke for SN2? See, again, water, alcohol, and a carboxylic acid are polar protic solvents. They're not nukes for SN2. They could do the SN1, but they're not nukes for SN2. But in this case, is there a nuke for SN2? You see a sulfur with a negative charge and no resonance. You don't even have to have check basicity over here. There's no need to even check basicity because that's a nuke for SN2. The reaction here is SN2. I want you to go through as many reactions as you possibly can and tell me if they go SN1 or SN2, both or neither. Some will go both. Some will go neither. For example, if I change this down here to H2O, then I have the solvent for SN2, for SN1, and I have the nuke for SN2. if I erase this and just have H2O, I don't have any nuke for SN2, but I have the solvent for SN1. Do you see? How do you know when you're done? When you no longer have any question in your mind, what's a nuke for SN2? Or what's a solvent for SN1? Find every single question you could find on this. Do as many of them as you can until you're an expert on knowing whether the reaction goes SN1 or SN2. Then when it comes to solving the products, it's like 2 quick arrow pushes and we'll figure out how to solve the products. And in fact, knowing how to solve the products for SN1, the major difficulty there is not the actual SN1 reaction or the mechanism or the deprotonation, it's a carbocation rearrangement, which I will teach you how to do. So anyway, stay tuned, hit subscribe, like, success.